Thanks. Hi, everyone. So I'm an IT entrepreneur, but also a fellow of the British Computer Society, or well, BCS, formerly British Computer Society. And I've done quite a lot of work in the recent years on, been involved with their work on data center energy efficiency. And I'll just give you a bit of a background on me. I'm a geek, so I started programming one of those when I was about 8, and sort of developed quite a passion for it at that age. In 2002, I set up Memset, my company, renting out virtual machines on short timeframes, which, as it turns out, was quite prescient. We've always been very focused on energy efficiency. So we were the UK's first carbon-neutral ISP, and as I'll show you, we've continued to drive forwards our energy efficiency. I'm also the chair of Intellect's climate change group. And I've been very involved in the G-Cloud program, which some of you might have heard about. Actually, Memset was one of the first companies to get involved with G-Cloud. And again, I'm going to touch on that again because security and efficiency, that's quite an interesting, some people say it's a contention, but actually I say it's not. I'm also doing a part-time PhD in the sort of area of cloud computing and energy efficiency. And I'm on the Green Economy Council. So Memset, my company, we're a hosting company or an infrastructure company. So we do basically the same stuff as Amazon. And we do it for some of these, those organizations, about 3,000 customers in total. We're also pretty good at it. And this isn't just me bragging, I'm making a point here. We're actually cheaper than Amazon. We dominate in the awards locally, but we're actually a very small business. I've only got about 30 staff. I'm only turning over about 5 million quid. So with the sort of steps I'm talking about, you don't have to be at the mega scale of Amazon and Google to actually achieve really very impressive levels of reliability and efficiency. Also, I'm not going to go on about this too much, but there's a lot of talk always about reliable quality of service, security, and that sort of thing. Actually, you can look to fairly standard ISO certifications for things like 9001 quality, 27001 information security as a basis for whether an organisation in the cloud has good security credentials. And indeed, government, with the G-Cloud programme, their security accreditations are mostly based around the ISO 27001 certification. So, you know, if you are worried about the security of a supplier, just use the same metrics you would to evaluate any supplier, frankly. Right, so how do we, and companies like us, how do we deliver infrastructure services more cheaply than most of you guys can do yourselves while still making a profit? I get asked this a lot. And actually, we don't do anything particularly secret or particularly clever. In fact, if anything, we've taken a very simplistic approach, which I'll go through a few of these in more detail. So the first one, this concept of internet data centers, which is relatively new. A few years ago, data centers were built with the idea of co-location in mind, principally. So, you know, you have a very narrow temperature tolerance, you rent out racks to people, and there was a disconnect between the mechanical and electrical infrastructure and the IT infrastructure. Whereas these days, the way companies like us are doing it, Amazon and Google are doing it, what they're doing is they're taking the data center and designing it around the IT kit, which might seem like a really obvious thing, but I mean, a very good example is nameplate versus actual IT load. If you look at the back of a server, it'll say one new server, it'll probably say 300 watts, which is the maximum capacity of the power supply. In reality, it will never take more than 120 watts, ever. But in the old school world, people would design their data centers around, well, what would be the maximum power if all the servers used what they said on the back? Because that's the sort of mechanical engineer's viewpoint of, you know, we want to make sure you delivered enough. So if you actually take that away and design it for what the servers are actually going to use, and you make some compromises like say, well, actually, if a rack's getting a bit too hot, we'll just put less servers in it and things like that. That helps a huge amount because it means you have a lot less power resilience and cooling infrastructure. I'm going to go into more detail about the unnecessary cooling and sensible resilience as well. Another really simple one is we fill our racks. Most data centers, they have very empty racks. You wander around Telehouse or something, there's loads of gaps everywhere. And again, that's very inefficient. You know, you want to be filling the racks, making the most out of the space. And also, I'm going to come back to the keeping the module size down. Now, don't get too scared by this chart. This is a psychometric chart. Now, the reason I put this up here is because there's been an evolution in the last few years. The reason data centers used to be built to deliver air between 20 and 22 degrees with 62% humidity is that very old machines were very sensitive to temperature and humidity. Modern servers are not. So we've all got computers at home. They don't mind when it gets a bit warm or a bit dusty or a bit humid, and actually nor do servers. Well, they do mind the dust. But ASHRAE, who are basically the American authority on, I think it's actually the Association of Air Conditioning Engineers or something. But anyway, they're the authority on the tolerance ranges for electrical equipment. They've now said that servers are okay all the way down to 10 degrees Celsius or up to 35 degrees Celsius, as long as the humidity is anywhere from 20% to 80%. So computers don't like it when it's very humid, because you get moisture on circuit boards and it rots things. They don't like it when it's very dry, because then you get electrostatic discharge. And they need a bit of a temperature range. They don't like to be too cold, not too hot. But actually, to be honest, most people wouldn't be comfortable in those temperature ranges. So that's the big change in recent years. And this is for all Class 2 equipment. So that's pretty much anything bought in the last sort of 2 to 3 years will fit within this. And the really interesting thing is that's actually quite close to British weather. So this is a typical meteorological year at Gatwick. Now, these... Basically, you see that the humidity never gets below, I think that line's about 20%. It does go up a bit sometimes. Sometimes you need to dehumidify the air a bit. But the key thing about British weather is it never gets hot and humid at the same time. So these lines here are the wet bulb temperatures. That's the temperature of something that's damp, basically. So even on a hot summer's day, when it might be 35 Celsius outside, it never actually gets above about 22, 23 degrees for the wet bulbs. So if something's damp, then it stays quite cool. And this means that actually, in the UK, you never actually need, with a modern server's temperature profile, you never actually need what's called mechanical cooling. So your fridge has a compressor in it, which it uses to pump fluid around that requires quite a lot of energy. Actually, with a modern data center, you can get away with basically having some cooling systems on the inside, some water to take the warmth outside, and then some big radiators outside. And when it gets really hot, you spray some water on the radiators, and you're done. And with that sort of change in approach, we're seeing dramatic improvements in the efficiency of data centers. It's getting away from this old school mentality that you have to have really rigid temperature controls. In fact, most of the year, fresh air cooling would be just fine. You'd have to humidify it or wetten it sometimes. The only trouble with fresh air cooling in data centers is that there are occasionally environmental events where you need to go to recirculation. So say if someone lights a bonfire outside, you don't want all that crap coming into your data center. And if you have the capability to run on recirculation, then you basically you end up with two systems, so it actually becomes more expensive. So in our sort of latest research, and we're working with a few companies in this area, we think that the best current solution is a closed loop system, a free cooling system. But I say you can get, as long as you don't mind your systems administrators wearing shorts for some of the hotter periods of the year, you really don't need mechanical cooling in the UK, and nor in most of Europe either, because most of Europe is quite similar. So yeah, resilience. This is another one. Now, lots of people think that Tier 4 is the way forward. So Tier 4 is where you have N plus N. So that means you have 2 of everything. So if you need 3 UPSs and 2 generators, you have 6 UPSs and 2 generators, just in case various combinations go wrong. That's really expensive. Also, it flies in the face of my earlier principle, which is keep it simple. We've seen actually quite a lot of failures where they've got lots of resilience in the infrastructure, but the control systems are so complex that actually when something goes wrong, it takes longer to diagnose, you have a longer outage. Also, our preferred approach, which is also Google and Amazon's preferred approach, is you have more than one slightly lower resilience data center. So you have a couple of N+1 sites, and as you can see, a couple of Tier 2 or Tier 3 sites are actually much more resilient than a single Tier 4 site. And a single Tier 4 site will cost more than twice the price of a Tier 2 site. So, and again, this is kind of a key tenet of cloud, I would say. Rather than trying to engineer against failure, you engineer to embrace failure. So you engineer your system to be distributed, so it can cope if this site goes down or this site goes down, and the overall can keep running. Just a quick thing on sizing. Again, mega data centres aren't actually terribly efficient or a particularly good idea. Increasingly, we're seeing people building to a sort of data hall size of around a megawatt. And this makes sense for a number of reasons. One of the main ones, actually, is data centres, generators. So generators, up to about the half megawatt sort of size, their price isn't linear. So because there's a lot of stuff, engines and gearing and so forth that you have to buy anyway. Once you get over about that size, though, the price starts to go up disproportionately again. This is because there are lots of roughly 550 kVA generators out there. They're called lorry engines. So that makes them really quite cheap. And again, the same with UPSs, in just the same way as, say, an 8 gigabyte stick of RAM is cheaper per gigabyte than a 2 gigabyte stick or a 32 gigabyte stick. There's that sweet spot with UPSs and sort of around the sort of 240 kVA mark. So that, to an extent, determines your size, but also a classic mistake we see is people building a huge data centre and then taking 5 years to fill it. And in the interim, they're operating their infrastructure at very low loads, which means they're very inefficient as well. So actually, it's quite a good idea to try and build things out in a modular, stepped manner. I mean, if you take a 1 megawatt facility and a typical 4 kilowatt rack loading, and again, actually, that is about right these days because servers have got a lot more efficient, and as I'll show you, don't really need blade arrays. That's a lot of servers you can end up in that space. So, trying to break that down into how many you're actually going to deploy each year can improve your efficiency a lot. I'm probably it's 5 minutes. Okay. So yes, looking at the hardware now. This is what we actually use to provide our virtual machine, to host our virtual machines on. As you can see, it's all quite cheap commodity hardware. I've also put in, though, the annual failure rates. So despite this thing only costing 500 quid, it's a Dell PowerEdge server, there's an annual failure rate of only 1%. They never go wrong. RAM also never goes wrong. Disks do go wrong, but we can hot swap them. So actually, just even at quite a low level, you don't need to spend a lot of money on hardware to get quite good resilience. Also, we actually found enterprise disks perform worse, interestingly. If you spend sort of an extra 30, 40 quid per disk, but actually you don't get any improvement in reliability. But also, again, with virtualization, the whole point is you have one virtual machine on this host over here and another one over there somewhere, maybe in a different data center. So without relying on any one bit of hardware for your resilience, you can get a much greater resilience, but actually at a tiny cost. So in a typical 4 gig virtual machine's 25 quid a month or something. Also, one of the things that we've learned over the last few years is that, contrary to popular belief, CPU is not the limiting factor in cloud computing and virtualization. So this chart shows basically the blue line is how much time the host servers spend at a particular. So you can see they spend most of their time in this spec at basically less than 10% activity. This is actually slightly old, this data, but we put a bit more RAM in, squeeze a few more in, and you can see it changes it a bit. But actually, the thing that becomes limiting is disk transactions per second. I think it was interesting to see there's a talk next about solid state estates, which I would say is definitely the future, and we do a lot of solid state machines now as well. But the point here is you don't need to put expensive and power-hungry CPUs into your virtual machine hosts. What's more important is to have enough spindles and enough RAM. And again, that helps to keep down your power and your costs. A sort of 3.5 gigahertz Xeon chip will cost you 3 times as much as a 2 gigahertz one, and it'll cost probably about 3 times as much power as well. Yeah, this just gives you an overview of where our costs really lie. Most of it is in the power and the data center, interestingly. So the cost of the chassis and the components is actually a fairly small component overall. We're busily working on this bit, though, because we think we can do a lot better. But yeah, you really shouldn't factor out those two. It's the hardware and the power and data center infrastructure costs will always be the biggest ones, and the ones that are worth looking at the most. Yeah, just a quick one here. We've actually done a lot of work with Surrey University on trying to improve our virtual machine energy efficiency, basically by looking at the sort of load bands, what the limiting resources are, and fine-tuning the hardware. And it's not particularly hard to do, actually, if you're interested in it. And what we've managed to do is, over the last, this is wrong, by the way, that should say 2009, that should say 2011. So basically, over the last couple of years, the blue line shows what Moore's law would predict our energy efficiency should have improved by. So Moore's law, as well as applying to transistor density, can be roughly applied to how rapidly the amount of computing per unit energy gets done. And actually, we're beating Moore's law thanks to kind of an intelligent and scientific approach to try and minimise our energy consumption. The downside is there's something called Jevons paradox, which is basically where when the price of something gets cheaper, consumers buy more of it, sometimes so much more of it that actually they end up spending more energy overall, and that's the average size of virtual machine that people are tending to buy from us. We are just winning, though, overall. So overall, our average power per logical server, with all the sort of measures I've talked about, we've gone from about, again, that should be 2009, that should be 2011, I don't know what's happened there. We've gone from about 50 watts to about 40 watts overall. So that's partly people moving towards virtualization, but we have the counterbalancing effect of people basically using more resources at the same time. So it's a bit of a fighting battle. And just in the last 30 seconds, we deliver all those enterprise services for those high-profile clients completely using open source software and open source solutions. We don't use any proprietary software anywhere. We use the open source Zen hypervisor, a range of other open source tools, OpenStack for our cloud storage. So you really can deliver enterprise services that are very efficient and also very secure using commodity hardware and open source software from efficiently designed data centers. And hopefully I've managed to convince you of that. Thank you very much.
Thank you, Kate.